Hi everyone. Today we'll talk about the integral calculus. Before we go there, we'll just do a simple recap of whatever we have seen so far. Okay, the machine learning, we started off with linear algebra. It is all about trying to find the relationship between two variables, relationship between the number of hours you study and the number of the number of marks you make. Relationship between the total number of goods you manufacture and the profit you make. Okay, relationship between the any two variables actually basically is what linear algebra deals with. And when you are struggling to find the relationship directly using the data, you do projections and try to kind of transform it from one form to another and try to get meaningful information from the relationship. That's what linear algebra is all about. Then we move on to trigonometry. It is trying to find the relationship between circles and triangles and how the rotation of angles in the circles creates waves, and it forms the sine and cosine waves, and how this relates to kind of finding relationship between two vectors. That's what we saw in trigonometry. Okay, and then we moved on to calculus, the differential calculus, where we studied about how a small change in input can make an impact on the output. Okay, so life is all about making small changes. Like if you make a small change to your volume knob in your radio, it creates a corresponding increase in volume in the speaker. Okay, if you increase the brightness of your screen a small extent, there is a small change in the brightness of your screen. So everything deals with changes. Okay, so the amount of change you make and the quantification of how the effect is what a calculus is all about. Okay, and in order to find what that small change, what do you mean by really small change? Okay, how does that small really mean? Okay, if you want to relate that, consider the earth we are living in. I gave this example, but still, okay, if you consider this as a circle, no, it's not no longer a circle, it's a three-dimensional, so it's a sphere. Consider this as it's no longer a straight line, it is a plane. Okay, so any point in this, if you are trying to find out how or trying to kind of get an intuition of how a point where it touches can actually create a slope. Okay, so just think of it as like a point you live in the earth. Okay, from the scale point of view, the earth point of view, it looks like very weird. But if you just try to zoom into the point where you live and place the scale in your room or the street, this becomes a straight line. Okay, even though it just touches a particular point in the earth, if you just keep zooming in and place this, that the point where it touches becomes a straight line, and that becomes large enough to kind of calculate things. Okay, even though it is infinitely small from this point of view. And if you look from the universe point of view, Earth is itself is a small object. So if you look at gas, it becomes a very small object. So if you think about it deeply, we as a human living in this universe are infinitely small objects trying to move here and there. Okay, from the point of view, so we still are able to do a lot of things, right? Even though we are infinitely small from the perspective. That's how you should think and visualize what you mean by zooming in and taking infinitely small spaces. Okay, and trying to make meaning out of it. Okay, so another way to look at it is just looking at trying to find a point here in the circle. Okay, that's again the same tangent. We start with two different points. Okay, let's say we start here. We try to find the tangent, sorry, secant, and then approach. Keep this. Let's say we keep this constant and keep creating multiple lines to this, and eventually you will form a line which touches this and it forms a tangent. So we are trying to approach this point and trying to reduce the distance between 2 points, and that's what you call well limits. Okay, this is the kind of background of all we have studied so far. Now we can extend this to integration. Okay, so let's start with an example. Suppose you have a car. Okay, sorry. Let's say you have a car and you drive from point A to B. Okay, point A to B. Okay, so let's graph this. Okay, this A to B is the distance. Let's say this is the distance in y-axis. Okay, and the time in x-axis. Okay, let's take 10 seconds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you're traveling 10 seconds, okay, from the point A to B, okay. What will be the total distance covered? Let's take that you travel at a constant speed, okay, just for sake of simplicity. Let's take, even though it's a distance, for every unit change in time, let's take this as a distance section. And the distance is, let's say, the speed is 1 meter per second, and the distance is traveled is 10 seconds. So if you remember the high school formula, distance is equal to speed into time. Okay, distance is equal to speed into time. So if you really want to find the distance traveled and if you know the speed and in the time, you can calculate it. Okay, like let's say the speed is 1 meter per second, the distance is time is 10 seconds. So the total distance traveled is equal to 10 meters per second. Now, if you look at this as a from this graph, okay, this becomes your length, this becomes your breadth. The length is your nothing but your the total number of seconds you have traveled, that is this length, and the height is the speed in which you have traveled for every second, and the speed is, let's say, constant here, and it's like 1 meter per second. So it's nothing but multiplying the length and the breadth, that is multiplying the length and the breadth gives the area of this rectangle, and this area of this rectangle is what your distance is. Okay, so if you, but here you assume that the speed is constant. What it really means is that you just start the car and you kind of take it to 1 meter per second and keep constant speed and reach there. But in reality, we don't. This doesn't work. Okay, we don't live in the world where everything starts and remains constant. So probably we'll start with 0 seconds when we start the car. Then we probably increase the speed, and then probably we maintain the speed, and then probably decrease the speed and reach the destination. Okay, so in reality, the graph is not a straight line like this, where you can find the area of the rectangle using length into breadth, but you will have something like an increase in speed and then constant speed, and when you approach the destination, probably reduce the speed and reach the destination. So now the idea of this rectangle and this area still remains true here. If you are able to find the area under this curve, you will still be able to find the distance. Now the only challenge is for every unit change in time, the speed is different. Okay, so this is if you plot the speed, this is the speed here. If you plot the speed, this is the speed here. So the speed is changing, and if you are trying to find the area of this curve, you will be able to still able to find the total distance traveled. Okay, now how do you find the area of something which is changing? Here it was very easy. We multiplied by length and the breadth. Okay, and when things are changing, and if you still want to find the area, that is where we try to use integral calculus to kind of make this intuition work actually. So let's say that this graph is changing over time. We still wanted to find the area of it. What we can do is we can try to create and break it into multiple rectangles, even though it is not a perfect rectangle. Okay, but the idea here is trying to break this curve into multiple rectangles. Okay, and each rectangle will have a width, that is your 1 unit change in time, that is 1 second, and each rectangle will have its height, that is the height at this particular point of time. So you can still try to add all these rectangles, even though it's not perfectly perfectly forming a rectangle. There is a triangle as well here. So here, this is a rectangle plus a triangle. So what you can do is you can break it into two areas. Okay, area of this triangle, area of this rectangle, and here it is like almost area of rectangle. And the idea is to kind of break the graph, which is keep continuously changing, into pieces of stuff where we can compute the areas and still add it. And that is what you mean by integrated. Okay, integrate all the areas and try to still find find the overall area of it. So the integral calculus is all about trying to find the area under a curve, okay, which is continuously changing by approximating those changes into approximately small rectangles. Okay, that's what it is. And here it can even do a triangle and keep up added. So, but now let's just restrict ourselves that it is going to form a rectangle. When you try to decrease the size of this bar. Okay, let's say I'm taking a huge bar here. Okay, which is its length and breadth. Let's say I bring it very close and closer and closer, and make it infinitely small, which means that I'll just form infinitely small rectangles with small change in dx. Okay, that is your change in time, and you will have f of x here actually. So what it really means is that if you're able to kind of find the area of this particular line, let's say it is a small change in x, and the corresponding point where it touches this graph is f of x. So if you multiply f of x into dx, that is what is the small the area of this line. Okay, I mean rectangle actually squeezes itself to form a kind of a very thin line, and you can still find the area of that thin line representing it as rectangle with length into breadth. Now, if we try to integrate between this point to this point, like let's say 1 to 10 seconds, then that's what it means by integrating the area of all the rectangles formed by this particular curve. So I'll write it once again. F of x integration is nothing but integrating the limits from, let's say, 1 to 10 seconds, this curve f of x dx. Okay, and f of x is the point, every individual point in this graph for every change in x. So if you multiply these two, this forms the area, and that is what you mean by integration by f of x dx. Now, how does it related to integration? Differentiation. I'll again give one more example. So here we have distance, we have time. So anything which changes with time is called rate. Okay. So anything which changes with length is called gradient. Okay. So let's say distance by time is equal to speed. Okay. So in other words, speed is equal to distance into time. Distance by time. Okay. That's what it means. I just read it. So anything which changes with time. So anything which changes with time is what we call as rate, and any changes with respect to something is what we call differential calculus. So this becomes ds by dt. Let's assume that the distance function is ds. This is distance by time, that is ds by dt. Okay, instead of dx I'm using dt because it is changing with time. So now velocity is, this is actually called as velocity if you have a vector. Okay, speed is a scalar quantity. Let's say if you are saying I'm moving at 10 meters per second, it is speed. If you are saying it I'm moving 10 meters per second towards east, then it becomes velocity. So we can call this velocity if it's having distance as well as direction. So this is velocity. Now rate of change of velocity with respect to time is called acceleration. Rate of change of acceleration with respect to time is called jerk. Okay, jerk. So imagine a car is going. If you change, you press the accelerator. What it means is that there is a change in acceleration with respect to time. Okay, that is called jerk. Okay, whenever you press the accelerator, there is some change movement in the car, that is called jerk. And the change in velocity with respect to time is called acceleration. Okay, so rate of change of velocity is called acceleration. So if you wanted to write it as a function of ds, here I've just used velocity and acceleration as two different functions here. Okay, you can call it as, this is like velocity is equal to ds by dt, acceleration will be d squared s by dt, that is the second derivative. Okay, and if you take the third derivative, d3 s by dt, then that becomes jerk actually. So you can represent it in two ways actually. This is the first derivative, that is velocity. The second derivative, which is the acceleration. The third derivative, which is the jerk. Okay. So you can keep changing. You can find. It is like this actually. There are many changes happen at the same time. You are trying to correlate all the changes and try to make an impact of one change or the other. Okay. Change in time. A change in distance with respect to time. That is what you see in the speedometer or the speedometer. Now, if you wanted to find the acceleration you make, you can have a measurement which is inside the car, and try to find the rate of change of velocity, and find the acceleration if you keep noting it down. Similarly, you can do it for jerk actually. So that's what it means. So how this is connected to integration. So if you look at let me write it this way: speed, acceleration. Okay, so this is ds by dt. This is d squared s by dt. Okay, this is change in distance with respect to time. This is change in distance, second derivative of it with respect to time, or you can write it as rate of change of velocity as well. Now, if you try to find, if you try to differentiate it, you will go here. Okay, if you try to differentiate speed with respect to time, then you will get the acceleration, and that is called differentiation. If you go from this direction to here, it is called integration. Which means that if you are able to sum all the changes with respect to time, you can find the if you are able to get the integration of all the acceleration with respect to time, you get the speed. Similarly, if you wanted to find the distance, you can integrate all the the graph I showed you, right? This is like you want to find the distance. Okay, you want to find the distance, and you have the time. Okay, you have constant speed. Okay, and every 1 second, 1, 2, 3, 4, up to 10 seconds, you have this speed as 1 meter per second. So if you wanted to find the distance, you are integrating all the the speed with respect to time. This is like one rectangle is like for 1 second, what is the change in distance with respect to with respect to time. Okay, so this is like ds to dt. Okay, this is just one single box. If you try to integrate everything, you get the distance. So if you wanted to find the distance here, okay, you can do an integration of this. That's what integration of this, and you will find the distance. So it is kind of a reverse. Okay, inverse operations. Okay, integration and differentiation of inverse operations. You can go from a variable, differentiate it, you get their value, and if you kind of integrate it, you can go back and get the value you started with. Okay, that's what you mean by relationship between integration and differentiation. So where all this is used in data science. Okay, this is for you to understand how integration works. Now, if you talk about any probability distribution, we will talk about probability in detail in the future, but just imagine you have a normal distribution which is like this, okay, and you will have a kind of a mean here, okay, and if you wanted to find the total number of the probability of certain thing event happening, okay, less than the mean, okay, and you need to find this is the total probability, this is the area under the curve. So this is how you would use integration to find area under the curves of probability distributions. This is nothing but similar to like the way we found the distance by using the time and the speed graph. Okay, and the same thing. Okay, we can relate it to each other. How area under the curve is related to the probability distribution. So let's you know that in probability everything should be between 0 and 1. Okay, so this point is close to 0. This point is close to 1. And if you wanted to find the probabilities of all the events happening up from 0 to this point, probability is 50%. Okay, and the area under the curve must be 0.5. And if you find the area of the under the curve on the right hand side, it is again 0.5. So just to sum this, you will get a distribution of probability distribution of 1 for all the probabilities under this curve. So this is to kind of intuitively understand how and where integration plays a role in data science and machine learning. Okay, thank you.